Good afternoon. My name is Martin Elliott. I'm a member of the SCITalk's organising committee, and it's my pleasure this afternoon to introduce Professor Jeremy Frey from the University of Southampton. Jeremy is there will be a Q&A session at the end of the talk, but Jeremy is an enthusiastic supporter of interdisciplinary research combining theory, computation, and experiment within chemistry, and through the science program, growing this to the wider computational and computing community, together with industrial research. Most recently, his role in the digital economy program through the IT as a utility network challenge area addressed the full breadth of interdisciplinary research connecting social, physical, and life sciences in a transactional context, bridging academic, commercial, and governmental areas. Jeremy attained his DPhil on experimental and theoretical aspects of Van der Waals complexes in PCL, Oxford, followed by a NATO CERC fellowship at the Lawrence Berkeley Laboratory in Berkeley, in California. In 1984, he took up a lectureship at the University of Southampton, where he is now a professor. His experimental chemical research probes molecular organization in environments ranging from single molecules to liquid interfaces using laser spectroscopy from the IR to the soft X-ray region. In parallel, he investigates how e-science, e-research, and cyber infrastructure can support scientific research, with an emphasis on the way appropriate use of laboratory infrastructure can support the intelligent access to scientific data. For example, the lab trove researcher-centric electronic laboratory notebook. Last summer, he had the opportunity to return to the Bay Area of California 40 years after his postdoc to attend the American Chemical Society fall meeting on harnessing the power of data and to give the opening plenary talk on Will or Not AI Win a Chemistry Nobel Prize and Replace Us? This afternoon, he will be talking about AI4U and what can AI do for you and what do you need to be able to use it. Jeremy, I'm pleased to be able to say the floor is now yours.
Okay, thank you very much, Martin. Thank the committee for inviting me to give this talk on AI4U. I will try and give a sort of an overview and oversweep of why it is that I thought an AI might have some chance of getting a Nobel Prize in chemistry, but hopefully not replace us. So let me start looking at this. So we're clearly looking at the transforming power of technology, but I thought I'd put some of the transformational ability of computers, which we all see, the speed up, the amount of memory, the number of flops and so on, in a little bit of context with some information here about electricity and light. And here is looking through human history, the amount of time it has taken to work to get an hour of light. And you can see from the way this has happened from prehistoric times to modern day, and in particular the way in which more recently there's been a dramatic change in even slope, actually largely to do with electrification, and just how huge a change has been occurred by this ability to produce light cheaply. So whilst computing power has changed radically and is changing hugely what we do, perhaps not yet reached the sort of transformation that just producing light has done, but we will see. Now, let's see if I can go. Okay. But in that context, here we have the plot of computer memory and storage falling. Actually, this is in that sense, the cost and the availability of storage falls more rapidly than Moore's law. I want to just put that as the background here against the fact that we did do work and research before computers. And the picture over here is what was until recently as I knew it, the John Hansard Gallery in Southampton. And actually that building was built of the tidal model. Those of you who know anything about the Solent know it has an unusual tide, and this was very important for the port. And this was in the days before the serious computers could model it, and they actually built a scale model of the Solent to be able to predict what would happen if you put sandbars and remove sandbars and so on. This was replaced in, I think, the mid-60s by a computer model, because actually it turns out Coriolis effects don't scale so simply, and the computer models were much better. Now, when I started my research, I did start with a nice traditional chart recorder, print out ink on paper, get out a little microscope lens and read off the dots and so on. But fairly rapidly, we got to use the BBC Micro, and that really was transforming the way that we could run our research. And then as that went on, more and more computers came into the labs, start using networks to be able to record data that was going on in the labs, to make it more and more efficient to actually undertake experiments. And then we basically came on to using a particular experiment you've heard I do use X-rays. These are laser generated coherent X-rays using a microscope, and the image recovery from that actually is not possible without a computational operation. We don't have X-ray lenses. So as a result, we started from the 1950s, computers were rarely used, they became useful, and then they became essential. And then, well, are we going to get to the point where this is an image of the Materials Innovation Factory up at Liverpool, where all the computers and robots sort of take over and run the experiments on their own? Well, we'll see. Of course, we in particular want to focus not just on the use of computers, but the use of computers to run artificial intelligence. And AI sort of came into being at the very beginning in the 1950s or so, 1960s, I should say, first AI boom. A lot of interesting work going on there, expert systems and so on. But by the 1970s, we had the usual way in which funding works around the world, that there was the first AI winter, because in some senses, the AI there did not deliver. And that we'll see was probably a technological problem in terms of sheer computer power. We'll look at the data aspects in a bit. In the 1980s, 1990s was the second boom, a lot of work going on then. And then the 1990s, again, a bit of despair. But then in 1970, you have Deep Blue playing chess, being now starting to beat Kasparov and are really showing the ability. 2011, IBM wins Jeopardy, quite an interesting application there of computers. And then we enter the real transformation where we go into the machine learning areas and the particularly deep learning. And we'll see that required a lot of data. And that data could come by machines playing themselves an awful lot of times. So AlphaGo, for example, became a fantastic engine for playing Go, discovered new things, but it played itself millions and millions of times. It's hard to do that much chemistry. But sometimes we do have a reasonable amount of data. And when you have all the data from all the experiments to determine protein structures, fortunately all held in an archive, the Protein Data Bank. Interesting histories there about how that's been maintained. But the data in there allowed DeepMind to model this to produce AlphaFold and AlphaFold 2. And that was a real transformation, and it has been a transformation coming now, and the data available for that is often the starting point now for investigations of any proteins. But we've also seen a further huge change in the last year or two with the AI chatbots and so on, the ChatGPT and its equivalents, these huge large language models. And I'll be talking a bit about those later on as well. So a lot has been going on, up and down a bit, and now we have some amazing engines that do AI. And of course, we do have to ask whether anybody's using this sensibly. We see that over the last few years, a significant rise in the number of papers published that are mentioning AI, machine learning in physics, chemistry, and material science. So it's from about 2017, a big upkick in that. Some of these are doing things that could be done more simply other ways and producing not terribly interesting results. Others are producing quite startling results. And so there is always a bit of a worry here. And of course, we have to remember that when you start inferring anything from data, we are back to the correlation and causation issue. And the traditional chemistry models have used this, and this doesn't change just because you have more powerful engines. And I always like this one because I'm a little bit of a chocoholic. And one of the first big grants we got in the eScience program, I'm sure, was helped by the fact that we were talking about chocolate polymorphs, and the chair of the panel was definitely eating chocolate at the time. And you can see here that the correlation between chocolate consumption per capita per year and the number of Nobel Prizes in that country is surprisingly linear. Actually, if you look at the milk consumption, it's a quadratic. So my suggestion is, unfortunately, it's dairy chocolate. It's milk chocolate that seems to be the most important. Can't really believe that. The health benefits from dark chocolate seem to be better. So, buyer beware in here. Be very careful about what you feed in and what you interpret coming out. That is true of any of the models. And I just make a note about some special things that I consider about chemistry. We have the traditional statement from the statistician box that all models are wrong, but some are useful. And I go on to say that different models are useful in different circumstances and for different audiences. And sometimes we use more than one model to deal with the same problem. Sometimes useful to look at a model from a number of different perspectives using different models. But what I think is rather strange about chemistry is sometimes the model we use are mutually inconsistent, even though we use them at the same time. And the ability of a chemist to hold these qualitatively different and often inconsistent models together is something that marks a chemist out, I think, from most other disciplines, and is why actually quite a lot of chemists go into accounting and various other things like that. These explanations, they flow back and forth between very rigorous mathematical style, the physical sciences, to more categorical ones of some of the historical, biological, and medical explanations. We use all of these. This inconsistent explanations principle is character of chemists, and as I say, is important in their training. So when we ask, as you'll see, the machine learning and the AI to explain why some things that it's predicting happen, many of the types of explanations are not yet, I think, suitable really for chemists. We are different about how we want to explain things. Now, why might we be interested in using AI in chemistry? Why have we been interested in computational work and so on? This is just one of many sorts of diagrams that can be found showing the increase in the cost of developing a drug. If you like, easy targets are known, it's costing a lot more. If we go to personalized medicine, it could be even more expensive. So we need different approaches to bring these costs down to solve many of the global problems that we have. And in 2020, the IUPAC competition to identify the top 10 emerging technologies included AI as one of the top things. It, of course, came out top alphabetically. And then following that, 2021's blockchain, 2022, VR modeling, and most importantly, 2023, it was these large language models being used in chemistry. So you can see that there's really quite a lot of background here to the belief that the AI, and in particular machine learning form of this data-driven science, which chemists were right at the beginning. Mendeleev's periodic table is a data-driven idea. And we've been doing this quantitative structure activity relationships for a long time, and these since the early 60s. So what is going on here? What is different about what the chemists are doing now, or can do now, compared to what they did in the past? Where here's an example of some work we did to look at drugs going across membranes and correlating them with their hydrophobicity. Well, if I'm being a little bit flippant here, I might characterize what we've got here as, well, if you've got relevant data and you know it, and you've got an equation or a model that you know, then that's called theory. I would say that's a lot of the physical chemistry that I do and used to do. If you don't have the data, but you've got a model, that's an unproved theory. If you've got the data, but you don't know the model, well, that's where the statistical modeling comes in. And that's QSAR and machine learning based on that. But in some cases, you don't really know what data is relevant. You've got a lot of data, but you're not sure what's important. And you've got an equation. Well, you've got lots of different equations. You don't really know what sort of equation. So you have some flexible system, and that we might call machine learning. So this is the Rumsfeld idea of known unknowns. And I think it carries a little bit of an idea of what's going on in machine learning. Now, some of the fundamental things that I'm sure all of you have heard about, these neural networks, artificial neural networks, ANNs, actually these go back to the early 70s, and some of the ideas really by the late 70s, early 80s, the backpropagation, the ability to fit data had been really quite refined. And they were used by chemists to predict spectra, to predict some bits about protein structure and so on. But the real change came from the 90s when computer power started to rise, and these things started to be able to solve the Schrodinger equation, solve for understanding heterogeneous catalysis and so on. And it's interesting to note that in that meeting that was referred to in San Francisco that I was at, the person, Heather Kulik, followed me, and she had looked back, and the meeting, the 203rd ACS national meeting, which was in 1992, also in San Francisco, had a section on chemical applications of neural networks. The titles, some of which are there, could easily be titles that use now. One of the differences, though, is the length of time it needed to run it, and the amount of data that could be plugged into these models, and the amount of data, indeed, that was available to put into these models. That's what is perhaps one of the biggest changes between then and now. Now, I have a computer science colleague, Naranjan, who is big on machine learning, and he would maintain that this is all you ever need to know about machine learning. We've got data, approximation functions, you've got estimate parameters, how you're going to predict things. Regularization, very important. We're taught in the early days, don't have too many parameters. Well, there are ways of keeping that under control, and there are ways of using models with very large number of parameters, potentially even more parameters than you have data, something that was certainly seriously frowned upon before. Not always brilliant, get also issues of overfitting, but really all this mathematics here is what's going on in terms of fitting, learning, improving, working around models, and we'll see some of these happening in the next few slides. But one of the fundamental concepts is, as I see it, is that we need kind of what we're all seeking for is a map of chemical space. How does the structural view of chemistry and what's going on there, whether it's a molecular one or extended molecular things or mixtures, depending what phases you're dealing with, materials, going to devices, how do we understand where that chemistry relates to some function? And this was often loosely called chemical space. I prefer the idea of chemical space-time. Time has always been critical to chemists. Transformations are what chemistry is about. But either way you look at it, misquoting Douglas Adams, chemical space is big, it's huge. And I discovered when I talked to some geographers and gave them a talk a few years ago, that there are laws of geography. And one of them is really quite interesting. Everything is related to everything else, but near things are related more than distant things. And that kind of works for chemistry. This is Waldo Tobler's first law. The problem is, actually, we have a bit of problem understanding what close is and what similar is in chemistry. And there have been books written about that. But what we can all agree on is chemical space is huge, and we're going to end up with a lot of data if we got a reasonable, even a reasonable fraction of a bit of chemical space made. We're going to have a lot of data. So that usually then gets quoted as the problem we have of the tyranny of the chemical space, the size of it, and the problems of huge dimensionality, as well as huge amounts of data. But I would like to point out that sometimes lots of data and big dimensions comes to your help. This is the central limit theorem. If you've got enough stuff and enough size, everything becomes Gaussian and simple, and we use this all the time. So sometimes large bits of space and large numbers of molecules is useful. But at other times, the curse of dimensionality does hit you. And one of the difficulties is that as you go up in the number of dimensions, almost all your data points end up on the edge. It's really quite difficult to characterize a space with a large number of dimensions without ridiculously large number of molecules. A peculiarity, if you ever want to pass this on to those people who perhaps can't visualize in 25 dimensions, is that the volume of a sphere surrounding a data point versus the volume of the unit cube around that actually gets a maximum a dimension of 5 and then starts to disappear. Very strange behavior. And this causes all sorts of problems about the way in which distance measures all go wrong in very large dimensions. Things can be a long way from each other, and they always look a long way from each other, and it saturates these things. And so actually trying to model how close something is becomes really very tricky. So one of the things we usually try and do when we have all of this data, which we think might be useful on a reasonably large number of molecules, which we think might be representative of our space, is we want to try and collapse this all down to reduce the number of important dimensions. And dimension reduction is critical to the ideas of machine learning. Squeeze it down to some latent space in the middle. Now, all those might be a puzzle to many chemists who've never looked at that, but actually my belief is that chemists have seen this all the time. So probably remember from days of thinking about the physical chemist kinetic model of gases, all these molecules, around 10 to the 23 of them wandering around in a vessel. If we had to keep account of all 10 to the 23, we would be in a lot of trouble. But we don't, because the ideal gas law works pretty well. PV equals nRT. We've gone from the statistical thing, 6n dimensions, where n is the number of molecules, to PV on n and t. Now, sometimes you need a bit more detail, and there's a bit more than there, but that is a pretty neat dimensional reduction. In other cases, now I'm going to bring up the next picture. You might see an initial transient and then a slow movement of the dots. And here, no, actually, it's hard to see. So this is the Michaelis-Menten steady state approximation, and there we go. It zooms up, very quickly getting to the steady state, and then the whole evolution takes place on this one curve. Again, dimension reduction, steady state approximation, that is a dimension reduction. Modern DFT is also a kind of a move from the individual coordinates of the electrons, worrying about all of those, over to an electron density, which is largely then a density in 3 coordinates. All of these things are kind of dimension reduction and show you that chemists for many years have been using this idea of the critical smaller dimensional space that actually governs the chemistry. Just to give you a bit of amusement here, and looking at the idea of augmented intelligence using the AI alongside our brain power, we had an idea, and I've had a student who's been very successfully doing this, of resurrecting what might be called a zombie notation, the Vice-Versa line notation, because it contains a lot more chemistry than the SMILES notation does, which is just telling you where the atoms are. So we did this, and one of the problems of using it is that there are a set of rules written down in a few books, not known by many, quite difficult to do. We want to get this working on a computer. So we thought, oh, right, we'll go and get hold of as many WN smile string pairs as we could, get them out of PubChem, ChemSpider, they gave us all of these things. So let's train a model. And we trained an artificial neural network. Didn't work too well. Then we discovered that Roger Sale had written a reader that reads most of the WNs, so we could generate randomly large number of things and check that they could be read, filter out the ones that could, and use that to make enough data so that we could make a neural network, which sort of worked. We then tried a transformer technology that worked a bit better, and then from Wendy-Weil, we managed to obtain the books that gave all the rules. And what it discovered is actually the problem was not so much with training our networks. The problem was with the data. There were things wrong with quite a lot of the data, misapplication of rules, strange things that had happened to the data that over the last 50 years had got maneuvered around. So we fixed some of the data, then discovered the readers work much better. And now, understanding that and working on what's going on, we have developed a whole model of the rules, really nice, effectively a compiler, and we can now transform SMILES into WNs and back again. And that's software that Michael Blakey will be releasing as part of Open Babel. And now we've basically gone, if you like, from a machine learning system that taught us what was going on, found out what the problems were, to an expert system, if you like. And we can use that with our models because now we can provide the various other models that we're training to predict properties with chemically intuitive information that we have programmed in. So this is a combination of data-driven and expert-driven work. So what though, I've already alluded to this a little bit, what makes the really big difference between, if you like, the pre-2000s and now is deep learning. It's using very big models, which use lots of data. So when we have lots of data, we can use these very big models with lots of parameters. We can effectively train them because we have big GPUs, we can do it all. So when we have more data, we have more data and we can use more data. In those cases, AlphaGo and so on, you can use these deep learning models very effectively. But rarely do we have enough data in chemistry. So the best is when we can have a reasonable amount of data and we include chemical insight, chemical models. These are often called physics-based models. I object to that because what we use here is, yes, some physics-based, some maths-based, but very definitely chemistry-based models. And that's what's built into, for example, the various different pipelines that are involved in AlphaFold 2. So where is this data? What's going on? Well, we have nice repositories, fortunately. Small molecule, the Cambridge Crystallographic Center has the CSD, and we have the protein data bank, the PDB. And I've plotted here the rise scale between the two of the structures that are going in. Of course, there are far more small structures known than are in the database. They're privately held, but this gives you an idea. And in fact, can see that it does look like the PDB is climbing faster now. But on a log scale, it actually looks like in a mature area, the doubling time for structural data here is something like about 16 months, which is quite good because that's longer than the doubling time of computer memory. So we shouldn't have any trouble storing these structures. The problem is getting them. So that at least provides some hope that there is data appearing there that can be used by the chemists. But data is a big deal, and understanding where that data comes from and how we can produce it. So I do some teaching in environmental chemistry, and I've put up here the hydrological cycle, which is something I deal with. And I can, by sleight of hand here, transform that into the datalogical cycle. These are all the things that happen to the data. And I'm sure any of you who either make data, collect data, or even better, responsible for people who do this will have seen, oh, well, let's, how do we manage the data? We can put it into a data lake. If it's get bigger, I call it data ocean. We can stream that data. We've got archives that are put away and quite difficult to get hold of. Big interest in data clouds now with all the computational power and data fogs around, which is a kind of a version of that. And it might rain data occasionally, usually doesn't. And then we have the underground passage of data. That's a very useful one. I've got this data, I'll give it to you, but nobody else knows anything about it. But perhaps the biggest one that is the biggest fear of fellow academics is the evaporation of the data when the PhD student leaves. So this data, it's really valuable, and making sure we record it properly and keep it properly and make sure we can find it, make sure the metadata is there, make sure the uncertainties are known. This is utterly critical. Otherwise, rubbish in, rubbish out. We know all about that. I was told that there's not quite similarity between the water and the data because there are limits to the amount of water on the planet. But actually, we do get extra comets apparently dumping water in, did in the past, and erosion of the atmosphere with the solar wind. So maybe there is a bit of a greater similarity. Now, one of the difficulties and the bugbear of all the data scientists here is that there are so many formats of data, and you spend more and more of your time exchanging and changing and transforming the data so that you can bring all the different data sources into alignment and use them. Very clever people managed to produce these sockets here. These are lots of all the electrical socket issues when you go abroad, but there are some now sockets that will take multiple different types of plugs. More and more we're moving towards that. And that's one of the things of the Physical Sciences Data Infrastructure project that I'll mention later, is trying to look at some of these standards and trying to help people align things so that their data can be used by others and that they can use other people's data. I will highlight the really important thing about data was perhaps not always called out. So it might be a surprise to some of you that the OECD, an economics operation of developed countries, actually produced some principles for QSAR modeling, particularly for toxicology prediction. And these were all really fundamental and very important ones. But only recently did a paper come out to point out that they needed an principle 0, which was to actually characterize the data to start with. And then that feeds on into the other principles. I certainly recommend you looking at these principles if you're doing any sort of modeling. We're hoping that IUPAC might just update these and publish them for machine learning soon. So one of the issues here is, we do need all this data, and there's a certain level at which we're kind of talking about making haystacks to find needles. We have to be careful about this. It seems like a good idea to make lots of data. We need lots of data, but lots of relevant data would be even more important. So at least getting some help in making the best haystack is going to be important, because we clearly can't make everything. And this is going to be one of the things that we have. So be able to be appropriately conscious of the environment and everything. We can't make it. So we need to reduce the number of experiments that we do. We therefore need help in deciding what to make. So if we have a good predictive model, that is going to help us decide what to make next. And then we can use that to create data. So we can now access this quality data and use that to build a better model. But to build a better model, you need the many good experiments. So to actually reduce the number of experiments, we need to do more experiments. So this is one of the reasons I highlight that for all the computational work that goes on, this is not going to do the synthetic chemists, or indeed, even just as importantly, the analytical chemists, the characterization chemists, out of business. Absolutely not. We're going to end up needing to make more things and characterize more things, but less of each one. And that is a huge challenge to those chemists. Now, what's interesting again from the data perspective here is can we use other data or the AI approach itself to help here? So one thing to do is to use transfer learning. So we have plenty of images of cats and dogs, which all of the image processing has been trained on. And that actually provides quite a good basis on which to train some chemistry images. We have lots of language stuff in the large language models, and that's very useful for helping it train chemistry. So actually we can get a kickstart with a lot of data, often from somewhere else. The more associated that data that we're bringing in is to the problem we want, the better, but it is surprising how much you can actually learn. And if you think about it, as a person, humans do that all the time. We learn from one area to the other. The other is so-called reinforcement learning, where you start off with some estimates of what's going on, make some predictions, and with some likelihood work out what you should do next to either get yourself into a bit of space that you don't know, or a bit of do some experiments that will minimize the uncertainty. So that's in spaces where you know the least. Some of this is in the human in the loop, for example, rather than saying do an experiment, can give you a list, and the humans will choose which ones they like. So for example, you might get a system might say, make the following molecules using the following type of chemistry. And I might say, I don't like that chemistry. I don't know much about that one. I'm going to choose this one. After a while, this loop will learn actually that this is the sort of chemistry you like. Now, that's putting in a constraint, but it also is a realistic constraint in the system if I'm doing the chemistry. But a lot of this data then is coming from laboratories, whether they are robotic or human or a mixture of the two. We need to get that data. We need reliable, well-defined, highly reproducible data. And so one of the critical issues in laboratories is that we do need smarter laboratories. And we can summarize this as AI needs IA. The information architecture in the laboratory is critical. One of the big annoyances that we find is we have rooms, labs, which are moderately well controlled in terms of temperatures and things with the building management system. But when we ask, can we have the data out of the building management system? The answer is no, you can't. So we end up resetting up a whole load of sensors to make measurements that are already being measured. But there's more equipment coming out now that measures the temperature in the flask and so on. This is all contributing to much better quality data, alongside with the high throughput work with all the other types of advances, flow chemistry and so on, all of which are allowing us to do more chemistry more rapidly on smaller amounts of material. Many people are restructuring their labs, thinking about what the labs need to do. There's a lot of work and thought to make labs really efficient places to work, to allow the people working in the lab to spend their time doing more of the interesting thinking and doing rather than some of the donkey work. The other place we can get data from is data that's already recorded, often in archaic systems in lab books, sitting in boxes where people think they've got valuable things. And we've started a company here, Data Revival. And one of the things we're doing in chemistry here is we think we have about 2,000 chemistry years of data in these Koch notebooks. We've scanned about 10 terabytes so far, and we're able to extract out a lot of the structures and read most people's handwriting and get the context and so on. We're working with our companies as well to do this. So, this is making use of historic data just as importantly as collecting new data. And pulling all of that data together, many of us here in Southampton and others have been explaining to the community and to the funders that it's really important to be able to store your data, get this right so you can exchange data easily. And the life sciences have done a lot more of this. And we've now got a project here, the Physical Sciences Data Infrastructure Project, led by us in Southampton and the STFC Computational Science Division, to try, if you like, and make sure the physical sciences catch up to provide data, the physical science data, to, for example, the life sciences, material sciences, and engineers, and so on. Well, one of the interesting areas, this area that has blown up is, chatting to the computers and so on. A bit about the social media here. So tea rooms are the heart of chemistry departments. I think there was a heart of chemistry operations in industry too. And one of the things that we recognized going back to the 2000s was the increasing growing need for a virtual tea room, so you could talk to colleagues who were not with you, but still have similar experiences. And in some sense, COVID mitigation strategies were built on these online collaborations. Zoom took over, Teams, so on. It's not the same as having a cup of tea with people, but like I'm talking to you now, it's better than not talking to you. But now with the rise of AI and machine learning, we've got all sorts of things you can talk to and get interesting answers from and discuss with your colleagues. And ChatGPT is one of the early ones. There are others now that are amazing when you ask them the right sort of questions. And before anybody says, yes, but they hallucinate. Yes, well, so do some of our colleagues as well. And they are biased, and so are some of our colleagues. As long as you treat these like talking to a person and understand the limitations of that and the extraordinary things that people and these models can do, these are things to be investigated. And they are transforming the way that we work. They're extremely powerful, these large language models. They're also huge, but somebody has done the training on them, spent huge amounts of computational power to allow us to use them quite easily. So we do have a significant dilemma for teaching, because was this answer from the student or was it from ChatGPT? This is an issue, but we faced this before with Google searching and Google Scholar. So, we will have to develop ways of training people to use these tools properly. By the way, if you think that there's a security problem because if you start using these things, it's going to ingest your data. No, there are now systems here where you can take the basic model and train them a little bit on your own data. You can use them on your own machine, and you can give it a packet of papers, whatever documents that it will ingest and use, and it will answer the questions from that. You need to understand carefully how to prompt it, and get it to do what you want, but it will only draw from those documents you gave it. So, no need to worry about it inventing stuff. And one of the things it will certainly do is, I believe, is to be able to deal with extracting data, manipulating data, moving it around, doing a bit of the programming, the heavy lifting, the boring part of the data science before the real insight comes in. These models are fantastic at doing. Now, you shouldn't be, they may have some problems, but may I point out, so do we when looking at literature. This is an area I looked at for long, looking at liquid surfaces. And here's a very nice paper saying the water surface is acidic, followed by a paper a little while ago saying, no, it's full of hydroxide ions, and that actually the surface of neat water is basic. There are contradictions. People measure things. There are good reasons, actually, for this particular dilemma. But this is just an interesting case where the literature is divergent. Models need to be understood. And don't be surprised if the data extraction techniques get a bit of wobbly there. So do people. But what it really gets back to, again, is the need of explainable AI. We need to understand why the model got that result. Now, if you're in the middle of the pandemic and you would like to know what next drug to give to somebody to dampen down their immune system so that they survive, you'll try the next thing and see what, as long as it's safe, it seems to be safe, you'll try it. And that seems sensible. But when you later on have you actually want to understand why it did it, that's where we need these explainable models. We also need, ethical models, the same as anywhere else. Any of these models that might or may not give you your insurance claim or whatever, we need to know if they're biased. Well, the same thing comes in the prediction of the chemistry. Did it give that result because it was biased, because it was only trained on a certain type of chemistry? These things are just as important in fundamental science as they are in the ethical applications of AI in the community. Now, this question about whether the Nobel Prize, of course, I was wondering about it, thinking about it. So I asked ChatGPT a while ago, and will the AI win a chemistry Nobel Prize? And it came back and said, can't really predict the future. Certainly AI can contribute significantly to chemistry that could be awarded a Nobel Prize. In effect, certainly with a lot of computation, it has. But it then comes back with this note that it's important to note that Nobel Prize is awarded to individuals or groups of individuals, not to machines or algorithms. And I thought this was a bit of a nice touch in a rather sort of sympathetic way, feeling a bit hard done by. Even if AI plays a critical role, the prize would likely be awarded to the human scientists to do it and applied the AI methods. I think if they develop them, it's one thing, but applying it without developing. So I think there's a certain amount of feeling behind ChatGPT. And we need to take that into account. I'm always very polite when I talk to ChatGPT. Now, some of this has been foreseen. So Robert Heinlein, who was quite a strange individual, but wrote some good science fiction, wrote in the 1950s, when chemistry becomes a discipline, mathematical chemists would design new materials, predict their properties, and tell engineers how to make them without ever entering a laboratory. Well, I hope not. I think those chemists should always know much about how to make the chemistry, but it's not even clear that anybody will enter the laboratory. We now have these robotic laboratories, which might make it without that anybody going in, but you certainly have to tell them what to do, or maybe not. So Ross King has a system in the biological application where actually the AI starts to develop the hypothesis as well as undertake the relevant experiments. But I think we're quite a long way from that being used significantly in chemistry. What I will say, though, is that there's a huge cultural change, bigger than the ones of bringing in computational chemistry, simulations, quantum chemistry calculations. We will see a huge cultural change. We, as chemists, need to adapt yet again to using and making the best use of this environment. So, watch out for that, nurture it, learn, senior people. We had hoped to run a doctoral training center where we would have the young upstart kids who knew about the digital but knew nothing about what it meant really to make a drug, mixed with those people who may not know the digital but certainly knew what it was to do the chemistry. Unfortunately, we didn't get that funded, but I still hope that we'll get this mix and those two groups. I'm being a bit stereotypical there, but can learn from each other. They've got a lot to learn from each other. So thank you very much for listening. I do hope that whilst as it says here for the New Yorker cartoon, that the superhighway here, we can talk over, it's been great, but the art of the schmooze is really important. It's quite hard to convince you really of the passion I have for this over the network. But I hope that it will have some in-person meetings soon, more of the SCI's digital group, to talk about this sort of applications in more detail and understand the pain points and pinch points that people have and see what the sort of digital machine learning models can do. And I'd certainly like to thank all the brilliant members of my research group over the last 40 years and colleagues across all the disciplines that made all of the work possible that led me to have these views. And it is really important. We've got a lot to do. The environment, the climate, all sorts of things that we have to deal with here. And we don't want to be sitting around like those dinosaurs and not have any solution to the problem. Thank you very much.
Many thanks indeed for a very, very interesting journey through the AI world. I was certainly expecting to hear about things such as the physical science data infrastructure this afternoon. What I wasn't expecting was to have been taken via the tidal patterns of the Solent and the health benefits of dark chocolate. With Donald Rumsfeld's unknown unknowns thrown in to make it even more interesting.
Well, as you know, as chemists, we're very widely read.
Right, let's have a look and see what we've got coming through on question and answers. So, okay, please keep them coming, but the one that we're going to start with is, which is your preferred format for analytical data?
Good question. So the important thing about a format of any format is there should be enough information to contain the context for that analytical information, and it should be well enough described to be machine readable as well as human readable, one way or another. With particular analytical data, allotrope, for example, has been quite a leader in the use of these XML forms. So I'm a fan of these sort of semantic web technologies that have ontologies behind them and so on. And that's pretty, those are perhaps the best case when you can have a full machine description. But actually you don't need to go that far. What is really important is to use a widely adopted format that people can easily interconvert to get it into the format they want. And so you've got to be able to look up, the things have got to be well enough described. It's nice when everything just falls straightforwardly. So if we take the crystallographers as a real example here, because they're, with the CIF format, there's the crystallography data is well described, it's really useful, but they have all sorts of other interesting data in there, like the melting points. But when you, at the moment anyway, I believe this is going to change, when you download that column from the database, it's got the units mixed up in there, it's got uncertainties in there. You have to spend a little bit of time unscrambling that, but actually at least it's possible. It would be nice if you didn't have to do that. So that's why these systems where the machine readability is really high are fantastic, and it saves a lot of time because you can pull it all in. But anything at least that is well described means that even if you have to spend a bit of time, you will be able to deal with it. So I'm not out to make everybody provide every detail in my format. I am out to persuade them that they should at least declare what the format and what the details are so that I can extract their data. I hope that sort of gives a bit of a feel for where I come from. And actually in the physical sciences data infrastructure, one of the strands in there is to advise people about that, how to do that. How does your community, it might be a really big community and already done, or you might be part of a small group worldwide, just a few of you doing these critical experiments and need some help in conveying those experiments in a way it's the machine readability without losing too much of the human readability, which is important.
Are you finding you're able to turn historical data into proper structured data, the process as well as the chemicals and the results? With the curious what is coming out of data revival.
So the answer to that is yes. Clearly, I mean, we are taking handwritten stuff, digital documents. So others, Jackie Collar, have worked on the literature and done extraordinary jobs there. And the literature tends to be well laid out and a bit formulaic, even if our strange chemical formulaic things make it quite difficult. Lab notebooks are a bit different. Clearly, we have come across some lab notebooks that are rather difficult to structure the output, but others we've been really very successful. Finding structures, finding the context, taking out graphs, getting those things. We're doing really very well, amazingly well in getting that data and starting to return that to those who use those lab books and would like to remember what was in them or index them in research groups and so on. It's not easy. And of course, there's a cycle of training. And then if you've got a set of notebooks that have been written by a group that has used a certain pattern, you can learn those patterns, and there's a little bit of cycling around there to optimize the extraction of data. The great thing about chemists is they often drew structures. So there are pictures as well in there, and we're really very good at getting out and giving you back a smile string or whatever for those. Yes, we also, things like annotations on top of diagrams that we can pull out. Generally, if anybody scribbled something on the side of a graph, that's usually rather useful and important. We're getting good at doing that too. Happy to talk to Nessa more about that and pursue that opportunity if she has any data she'd like to get extracted.
This was the first in the trilogy about AI, and on 27th of March, we have Ruth Misner talking to us about Bayesian optimization and design of experiments. So if you think you'll find that to be another interesting way to spend an hour, so please consider signing up as soon as possible for that. And we still have no further questions coming through, so with that, once again, I will say thank you very much indeed to Jeremy for a very interesting journey through the AI world. And I'd like to thank all of you for attending this afternoon's SCITalks, and wishing you all the best. Thanks very much indeed.